Thank you, Pauline. Hi, everyone. So today I would like to give you an overview of the project I coordinate. It's a Horizon 2020 project. So my presentation will be more of an overview than a detailed presentation, mostly because it involves quite a large consortia. So besides Jozef Stefan Institute, we have Heidelberg University, we have VUB from Brussels, we have VUA from Amsterdam, we have Ottobock from Germany, and then we have a small company called S2P, Science to Practice, and lastly a rehabilitation institute in the Netherlands, Heliomar. So also I enjoyed very much the presentation so far, especially those at the beginning, the neuromotor control ones. So mine will be much more applied but scientific. Nevertheless, there are many details hidden in my presentation, so if you'd like to ask me something more concrete, please feel free to do so. So did you know that out of more than 200 medical conditions, low back pain is number one? I also didn't know when we started to write this project that low back pain is the leading cause of workers' absenteeism just after common cold. And that the global point prevalence is roughly around 10%, so 10% of us is suffering low back pain at this moment. In lifetime, it's around 70% of us will have low back pain at one point. And which is the worst, I would say, is that in 90% of the cases, the reasons for the low back pain are unknown. So in our project, we are trying to create a scientific body of knowledge from biomechanics, motor control, computer science, robotics, to prevent the occurrence of low back pain. We are trying to develop technologies to monitor and to give feedback to the user, to workers, for example, who are at risk. We are trying to also make some robotic knowledge how to rehabilitate low back pain and also, of course, to diagnose. So just to avoid confusion, so in our project, we are working on the so-called stress monitoring system. So this is not an exoskeleton, this is just a suit that a human wears, and then he or she gets feedback about the probability of low back. Then we also developed the passive spinal exoskeleton, which is an exoskeleton I will talk about. And also we right now develop the active spinal exoskeleton, which I will completely avoid in my presentation. So this diagram shows the concept of SPEXOR project. Basically the gray boxes show the work packages within, and I will walk you through all these boxes and tell you a little bit about what's the work that we do in each. So the first one is about the biomechanics of low back pain. Here we would like to identify biomechanical factors that lead to low back pain. And we also, here we define implications for the design of these prototypes that I just told you about. In this work package we also define the measurement protocols to evaluate our devices. So let me show you this is a typical situation in a factory. This is a worker that needs to move these yarn bobbins which weigh up to 15 kilos. So this guy here is at serious risk that once in a couple of years he will have low back pain. So I don't know if you ever calculated the force that are in our back. So let me give you a brief example. So imagine this is you lifting a box 20 kilos. Okay? So the upper body is roughly 40 kilos. This is 40 kilos. The moment arm is 30 centimeters approximately, which gives 120 newton meters. And then imagine a box here of 20 kilos. With a moment arm of 50 centimeters. This is additional 100 newton meters. So in total is 225 newton meters. And for the motion itself, let's say roughly 250 newton meters. Okay? So if these moment arms are quite large here. And this is the spine here. And these back muscles need to compensate this torque. And the moment arm here is only around 5 centimeters. So if you calculate then these 250 newton meters, you get compression forces roughly around 5,000 newtons. So these forces are both in the muscles and also in the back. And so this diagram on the left shows, so these are two vertebrae, this is the disc. So between the vertebra and the disc there is so-called end plate. So if this compression force is too high, what happens is that this end plate fractures. And here you can see what happens. And on the right side, you can see these squares show the compression when this happens. And as you can see, this is roughly from 2,000 newtons up to 10,000 newtons. So this correlates heavily with the anatomical properties of the area of the vertebra and the density. So in simple terms, in our project, we want to reduce this. So we want to reduce the compression, which potentially could lead to lower occurrence of low pain. So of course, in the laboratory to measure, so we need to then to estimate these compression forces. It's quite straightforward. We have motion capture, device, we have very precise force sensors, the ground reaction forces. Then we have some modeling, and using models of the muscles, we can estimate these compression forces. We can further optimize this using the EMG measurement and other optimization techniques. But in reality, if we want to do this in a factory, for example, or at home, we need to measure these in a much more simpler terms. That's why we have this second work package, which is led by Otto Bock in Germany. And they are developing this musculoskeletal monitoring device, which monitors what we found here that it's important. So this is just a rough diagram. This is the system of IMUs, and some force insole sensors. One of the main challenges here is so what is the minimal set of these sensors that give us some valuable information? So this is just an example of a study did at Amsterdam. So let me briefly explain this. So the gold standard here is that you measure precisely the motion of the human. You have the force plate, and using the inverse dynamics, you can calculate then the stress here in the lumbar sacral joint. Another possibility would be that you exactly measure the motion of the upper body, and you have an exact force and torques in the hand. But as I said before, we cannot do this in factories. That's why we use IMUs. So these green boxes here, these are IMU sensors. So we investigated where and how much of these sensors we need to get some precise measurements, which would be good for us. And I will not go into details, but basically this B and C are almost the same, except that the C1 doesn't have any sensors at the legs. So the main message or the main idea here was that what we do is we calculate first using the accelerations in the sensors and the forces in the support. We estimate the weight of the load that the human is carrying, and then using inverse dynamics, we calculate the stress in the spine. And this diagram just shows a very important message, and that is that even if you have like a non-ideal measurement of the forces of the support, it's better to use them than to ignore them. So the thick line shows the gold standard. This line here, for example, shows if you only measure the kinematics, and this gold here or whatever, the yellow lines show the estimation if you have very imprecise insole measurements. So we are adapting this technology also now in our project. Then we have the modeling and optimization. So those of you who were here before lunch, Katja Monbauer from Heidelberg, she explained the whole presentation just about this work package. So I will not go into details. I just have 2 slides for those of you who were not here. So in that work package, what we do is we try to model the interaction between the exoskeleton and the human body. We try to optimize the parameters of the device, parameters of the interaction, and also we try to understand the behavior of those who have low back pain or those who don't have this behavior, and how the exoskeleton affects those that have or potentially have a risk of having a low back. One surprising thing which we found during the project is that there is almost no literature about how to or where to attach exoskeletons to the human body and what this means for a human. So that's why we did our own study, where we simply, as you can see here, pushed or pulled the subjects at different parts of the body, and then we we got some force profiles. I don't have them here, but anyway, so now we have a sort of map which can tell us how much, for how long, and where you can put the exoskeleton to the human body so that the subject can wear it, basically. So that was a really quick explanation. So once we have the models and the optimal stuff, we move now more to the engineering part, which is so in this work package we do the electromechanical design of the devices. As I said, I will only show the passive version. So this is a 3D diagram. So it consists basically of the passive spinal orthotic module. So this is the module that follows the motion of the spine. So here it's just a carbon fiber rod. Then we have the so-called self-aligning hip module. So this is to accommodate different proportions of the human body. And then we have the actuator. So I'll briefly go into these in all of these elements now. So these two figures show that the spinal orthotic module. So these are some special carbon fibers, and here above there are some 3 degrees of freedom joints that allow the subjects to move. I will show you the video afterwards. Then we have this self-aligning passive mechanism, which is basically 3 degrees of freedom, 3 rotations, which are in series, and this allows different subjects to use, and also gives some motion freedom that's very important, as I will also explain to you a little bit later. And for the passive actuator, it's basically the Makepa actuator, where you have a spring, a wire, and this is a cam mechanism, and by changing the shape of this cam, you can change the profile of the force. And this diagram is just a kinematic. It just shows the kinematic structure. As you can see, there are many degrees of freedom. Those in blue are those who actually exert force on the human body. All others are just to make our exoskeleton wearable, in the sense that it does not include, that it does not limit the motion of the humans. So this is the next part, which considers control. So you might wonder, why do we need control with the passive one? So if you imagine you have this exoskeleton on you, it has some quite powerful springs here on the hip, and you try to lift something, you would feel very much relieved. But if you try to walk with it, you would immediately say, oh, there is a no-go, because exoskeleton should know, I would say this way, should know if you're lifting your leg or if you're bending forward. That's why we are developing some motion classification algorithms with which we can basically try to predict what the human subject will do inside the exoskeleton. And so for this reason, we installed like a very simple mechanical clutch on the hips. So this clutch was provided by, so this joint was provided by Autovoc, and then we added some simple motors which can lock or unlock this clutch. And here on the left-hand side, you can see we have information of motion of the upper body and both thighs. And then we classify basically what are the motions and whether we can turn on or off the exoskeleton. So this is a video, a very simple one, where this student is now doing different motion, and here on the screen you can see our classifier, what the subject is doing. So this is a pure, so this one that you see is we are just using Gaussian mixture models to calculate the probability of what the subject is doing. We also use some hidden Markov models, but it turned out that this was too slow, so we are still with very simple methods. And central to all our work is the end-user evaluation, so we give a lot of attention to the usability of our solution. So this work is led by the Kinematic Rehabilitation Institute, and basically here we are trying to validate the solutions we build. We try to evaluate functional and clinical performance of the device. More specifically, we, for example, try to evaluate effects on the metabolic costs, on the functional performance, on self-efficacy. So if you are wondering what self-efficacy is, so I guess some of you had low back pain. So if you have low back pain, you are very scared to do things because you think that you will get it again. So this is the self-efficacy. So if you ask one with low back pain, can you lift this 20 kilos or no, then so this is the self-efficacy. and we also measure user satisfaction. So for this reason, we created like this is like a test battery, which is a battery of standard motions, and we evaluate then the behavior of the exoskeleton, the human, using these motions. So here on this slide, you can see one worker from KLM, I think from the Dutch airliner, and he's trying, for example, here on the left side, we measure how far away you can stand with your legs using this exoskeleton, and in the middle you can see some other performance, which is also not directly low back pain critical, but anyway, here is a simple lean forward or standing in sustained positions for a longer period, or squatting down on this side. So on this diagram, I have to explain this one. So the dark red one is a prototype that we bought on market. So there were some prototypes which were even simpler than our ones. So this is a Dutch company, Label. And then this light one is our prototype, the testing. And more up, the better our solution is. And below here you can see different tasks. And as you can see, if it's above 0, this is actually that the performance is better if you use the device than if you don't use. And as you can see, for example, for leaning forward, our prototype turned to be very positive. Also, for example, for sustained postures. While for most other tasks here, it's below. So it means if you're healthy, you try to avoid using the exoskeleton if it's possible. And of course, now in our work, beyond my presentation, we are trying to push these bars up above the level of 0. Which we were also, so this is also what we were very happy about. So we measured, so this is just an example of biomechanical testing done at the Netherlands. And here we measure different tasks. We measure the oxygen consumption, and we then imply this on the energy level. And we were very happy that our exoskeleton actually reduced the metabolic cost significantly. So these are some statements that I can be pretty confident in saying. So we made a device that basically reduced the discomfort in lower back. We also, our device, we show that it reduces the risk of getting low back pain. It also resolves some problems of similar devices. For example, the clutch mechanism makes it much more easy to use it, because it's not just meant for the tasks that reduce low back pain, but also for walking, for example, or sitting. And also, as I said before, it has a potential to increase the self-efficacy of those people who had low back pain in the past. So thank you very much for your attention. I'll be happy to answer.
All right, so any questions? Sure. Okay, I do have one question. When you were talking about the control part, where you like recognizing what the person, like the movement of the person, on how many person did you learn? Like have you checked how it generalized, and do you have to learn like specific models for specific persons?
So the answer is, it's not very simple, because we tried most of what you asked me, but what we are sticking with is now that we measure, each subject does some task that he's doing or she's doing every day. Just imagine it's in a factory, and for one day we record motion of what he or she is doing. And of course, we measure this with many subjects, like we measure 10 subjects. And it generalized quite well for the simple tasks, but not, for example, for the task of standing up and walking. So for this, we still need to be the solution to be very, individualized. And for this reason, we made some interfaces where the user can push some buttons and say, now I'm sitting down, I'm standing up, and then the method basically learns this behavior. But this is still ongoing work, that's why I cannot be more precise.
Okay, well, thank you.
Yeah.
No question. Okay, well, thank you very much. Yeah.
You're welcome.